Hi everyone, we're welcoming Henry Yuen from Columbia. Today, Henry is an expert on quantum computing and complexity, worked a lot on two-prover games or non-local games, as you like to call them in quantum. Aren't they local games? I always kind of feel bad about that term. Anyway, he's one of the authors of the famous MIP star equals RE work, and today we will hear some more interesting things.
Great, thanks, Reed. Hi, everyone. Thanks so much for having me here. I'll be talking about query separations between two complexity classes called QMA and QCMA, which are quantum generalizations of NP, and their connections, its connections with pseudorandomness. So this is joint work with some wonderful collaborators. Jiawei Liu is who was a postdoc at MIT, now she's at Fujitsu Labs. My student Sachi Mutreja at Columbia. So I'm not going to assume that everyone here is familiar with quantum computing or quantum complexity classes, so I'll try to go through the concepts slowly, so feel free to ask questions. So the main results that I'll be talking about is that following, distinguishing between whether an exponentially large graph, given oracle access to it, whether it has two disconnected components of equal size, or has a single expanding component. This is some computational problem. This separates these classes QMA from QCMA, assuming a quantum pseudorandomness conjecture. And the upshot of this is that, assuming this conjecture, this then gives evidence that quantum proofs can convince verifiers of statements that are much more complicated than what are possible with classical proofs. The quantum pseudorandomness conjecture that I'll get into, I think it's interesting in its own right, because it's connected to open questions about whether there are quantum speedups for solving unstructured problems. And also this, something called the Aaronson-Ambainis conjecture, which is about influences of low degree bounded polynomials. Okay, so first off, let me define for you these quantum generalizations of NP. So the first one is something called quantum Merlin-Arthur, or QMA. And informally, this is a complexity class that captures problems that are efficiently verifiable on quantum computers, where the quantum verifier gets a quantum proof. So it gets some collection of particles that could be in some highly entangled state. And based on this quantum state, it decides whether to accept or reject. Formally, a language is in QMA if there's this polynomial-time quantum verifier V, where for all yes instances in the language, there exists some quantum state psi, where the verifier will accept with high probability. And if the instance is not in the language, then no matter what quantum state is given as proof, the verifier will reject with high probability.
If this notation is unfamiliar, this cat notation, it's just a vector in some Hilbert space. Exactly,
right. So yeah, if you're not familiar with the quantum notation, ket size and quantum state, so if this is n qubits, this is some unit vector in the vector space of dimension 2 to the n. So these quantum states can get quite complicated, right? If you were to write out its full classical description, this would take a very long time. But you can have n particles representing this state. Okay. So here's just a picture. Both Merlin and Arthur get the instance X. Merlin will provide a quantum state to Arthur, who uses his quantum computer to decide whether to accept or reject. So this is quantum Merlin-Arthur. It's sort of a very natural generalization of NP. Where does it sit in the complexity landscape? So, here's some things that we know. This class QMA is contained in P space, example. It contains both NP and BQP. And of course, we don't know separations between any of these classes, but this is sort of what we think the picture should look like. And just to give you a feel for what are some problems in this class, the quintessential problem in QMA is something called the local Hamiltonian problem, And this is, a local Hamiltonian is a description of some quantum many-body system. You can think of it as some sort of quantum generalization of a CSP, right? You have local constraints on a bunch of variables. Correspondingly, you have a bunch of what are called Hamiltonian terms acting on small subsets of particles. And here you want to decide whether there exists a quantum state with energy at most alpha or energy at least beta. Promise that one is the case. Alpha and beta are separated by some inverse polynomial. This is a QMA complete problem. And this is very important because it's, first of all, it's, solving this type of problem is the bread and butter of what a lot of physicists do day to day. They write down some local Hamiltonian that describes a physical system that they're interested in, and they just, they want to understand properties of it. Like what is the minimum energy of this system? What is the minimum energy configuration? So on. Another problem is something called circuit equivalence. I can give you two quantum circuits, and I want to, they might look different, but maybe they actually turn out to be identical in functionality, right?
Can I say something just to clarify about the local Hamiltonian? It's just an eigenvalue problem or eigenvector problem, but the matrix is 2 to the n by 2 to the n, the input matrix. It's just given implicitly.
Right.
So this may not be clear.
So, circuit equivalence, Yuen tells that two quantum circuits are equivalent. This problem is in QMA, or rather to tell whether two circuits are not equivalent, it's in QMA because the prover can just give you a state on which these two circuits differ, right? You can just check. Group non-membership, this is an interesting problem. So this is a black box problem, meaning that the verifier gets access to some black box, which performs the group multiplication of some exponentially large group. And the verifier here is given, let's say, a list of generators for a subgroup and an element. And it's asked to decide whether this element is in the subgroup or outside of it. Okay. So, the subgroup itself might be.
Subgroup testing problem that Michael Chapman was talking about? Or?
Oh, is it related to that?
I don't think so.
Yeah.
I don't think so, but doesn't this have a classical, didn't Babai use the motivation for his MA class by this problem? Do you need quantum here? This doesn't, I don't think it needs quantum.
So I'll get to this. So it turns out that, so here we're talking about non-membership. If you want to prove that an element is not a member of the subgroup. And as far as I can tell, there's no MA or AM protocol known for this. But here, so it was observed that to prove that an element is not in a subgroup, there actually is a succinct quantum proof for this. And just to describe it informally, the prover can provide a uniform superposition over all group elements in the subgroup. And through somehow using quantum processing power, you can verify that an element is not in this subgroup. So this is sort of an example of how quantum proofs can help.
I guess it's in AM, not in MA.
Mm-hmm.
Because it's testing whether with this element you get a bigger subgroup, and it's a thing that within a factor of 2. So using this AM techniques, I think that's what Babai
Gotcha.
did in his original paper when he introduced some AM.
Okay, I see. Good point. So it's in AM, not known to be in MA, classical MA. It is in QMA, so quantum proofs do help. So I think that was sort of an interesting observation. Let me talk.
You didn't tell us names, so who is responsible for the last one?
For the last one, John Watrous came up with this protocol.
So first it's retired, but I think we're back in.
Let me talk about the second class, QCMA. So it's kind of a mouthful, but this is quantum classical Merlin-Arthur. What does the classical refer to? It's the same exact thing. Merlin is providing Arthur a proof, but the proof has to be a classical string. It's no longer a quantum state. We still have the same soundness and completeness conditions like in QMA, but everything is with respect, all the quantifiers are with respect to a classical proof. The proof has to be polynomial size. Arthur is still a quantum verifier. So Arthur can still use quantum computations to decide whether to accept or reject. How does this compare? Well, in terms of complexity classes, QCMA is a set of languages that is contained in QMA. That's because, one way of seeing this is that a QMA verifier can always force the proof to be a classical string just by measuring, the moment it gets its qubits, it can just measure all the qubits and it'll get some probability distribution over classical strings. But from then on, it's just getting a classical string for which it can verify the statement. So QCMA is trivially contained in QMA. What are some problems that are contained in this class? So less is known. I mean, QMA has been studied for 25 plus years, but QCMA, we don't have as many problems that we know that are naturally in it. So an example of a problem is a ground state connectivity. And here you're given a description of a local Hamiltonian, which again, as Avi was saying, it's some succinct description of a 2 to the n by 2 to the n matrix. But instead of deciding whether there exists a ground state with low energy or the minimum eigenvalue is small, you're given two polynomial size descriptions of ground states. Okay, you're promised that these exist. So by polynomial size, I mean you're given two quantum circuits that if you ran on the all zero state would generate the corresponding ground state. So you know that it has two ground states of low energy, but what you want to decide is whether there's, in some sense, kind of a connecting path from one ground state to another that keeps you within the ground space. Right? So a sequence of quantum operations that you apply on the first ground state that transforms you to the second ground state. And every step along the way, you stay within the, this low energy subspace.
And the sequence has to be short or?
It has to be short. So, well, interestingly, depending on whether you let the sequence be short or long, that actually gives you different complexity classes. So if the sequence is forced to be polynomial length, this is a complete problem for QCMA.
And the energy barrier is the same for both of them. So there is a bound on the eigenvalue. Right. The same eigenvalue in both, and you like to stay under it throughout the record.
Exactly, yeah.
Sorry, just to make this explicit. When you say ground state, you mean eigenvector. When you say energy, you mean eigenvalue. And energy barrier is that in every space you're just in the span of, can you maybe spell it?
Oh, sure. Yeah, sorry. I've going a little fast. So yes, ground state is an eigenvector of minimum eigenvalue.
Minimum.
Yeah, minimum or within, plus or minus 1 over poly, let's say. And when I say that you're staying within the ground space, meaning that, so a path here would be, a collection of quantum gates that you apply. So you apply the quantum gates and each time you get a new vector. And you're asking what is the energy of that vector, this is the quadratic form of the vector with respect to the matrix. So that's going to give you some number. You're asking whether that number is within plus or minus 1 over poly of the minimum eigenvalue.
When you apply a gate, you're not necessarily promised to be an eigenvector.
Not necessarily an eigenvector.
No,
Doesn't matter. So what are you still measuring?
Just the quadratic form. So, V transpose the Hamiltonian H V. So that gives you a number.
So that's the path. You're not inside the eigenspace. Well, yeah, you're just moving.
Yeah, but you're in some sense staying very close to the ground space.
So if you don't limit the length, then it's just a question of whether the subspace spanned by the low eigenvalue, the eigenspace of everything below a threshold, where, these two vectors are there, so it's by definition connected.
Right.
But you're limiting the third complexity of getting
Yeah,
from one to the other,
right.
generating one.
Why is it by definition connected? I mean, it could be that all the steps you make take you out of there and go back.
But it means steps, now it circulates the vector space.
So there are steps
You have to be local.
by applying quantum gates.
Yeah, so that's, yeah, but if you are allowed exponentially many states to go without getting.
But you're gonna move out.
So classically, an example of this would be what they call like reconfiguration problems. Like if you have two SAT assignments, can you get from one to the other just by local bit flips? Where each local bit flip stays, you know, a satisfying assignment. And that's not necessarily always the case.
No, but that's a discrete problem. Here we are in continuous space. There's always, you know, these vectors. I suppose you didn't care about the complexity of getting from one to the other.
Sure.
We still have to use these local gates, honey. But you can't just put it all into one big unitary and call that like one step of high complexity.
Yeah, okay, so that's like, that's exactly what I want to distinguish.
Yeah, that's another constraint. So this problem is in QCMA because if there really was such a path, then the prover could just describe here are the local gates, 2 qubit gates that you can apply, and it's, you know, at most polynomial length. And there is a way for the quantum verifier to just apply the gates by itself and check that each intermediate state does lie close to the ground space. Another example of a problem in QCMA is just going back to this group non-membership. So we don't know that it's in QCMA, but under some group theory assumptions that I think some people consider plausible, there actually is a classical witness to prove to a quantum verifier that an element is outside of a subgroup.
Are you going to talk more about the nature of this group theory assumption? Or
No, I mean, I can say a couple words.
Say one word about it.
So the group theory assumption is roughly there's maybe 2 or 3 things. The first thing is that you assume that there exists a universal explicit, what do you call them? Model groups, a universal explicit sequence of model groups. And I'll just mumble something about that because I don't really understand. It's a sequence of groups such that, you know, for each of these groups, you can efficiently compute the multiplication table. And furthermore, every finite simple group is isomorphic to one of these. So I think in some sense, this sequence of groups is, you know, if you had your hands on it, then you can sort of model every finite simple group and therefore kind of build up every group you wanted. And then the second assumption is that for each of these groups, you can solve the hidden subgroup problem efficiently on a quantum computer. That's not enough.
Is that believed to be true?
I don't think so.
No. Do you believe it?
I don't have an opinion. Yeah. Anyways, it possibly, and what's interesting about this, so even if you don't believe these assumptions, there is a protocol where the verifier makes a polynomial number of queries to the group oracle. It might have to do exponential time computation, but it's not charged to the oracle. So there actually is a polynomial sized classical witness that helps this verifier prove non-membership. So, you know, this short witness has information theoretically everything it needs to know to prove non-membership. The question is whether it has enough processing time to deduce this.
Well, but with the exponential time, it can solve the problem anyway.
So there's a black box group, meaning that it has to make queries to the group
So the number of queries will be polynomial.
Would be polynomial.
Yeah.
Okay, so all of this was just to sort of give you a feel for what problems are in QMA, what problems are in QCMA. And you know, natural question is, you know, how do these classes relate? Are they the same? Are they different? And really it's asking how useful are quantum proofs, right? And So even though an n qubit state requires 2 to the n parameters to specify, you can't naively use it to just pack an exponential amount of information into the state, and the verifier can unpack it and use it. So there's something known as Halelo's theorem, which says that an n qubit state can't be used to convey more than n bits of classical information. And there's also many examples of problems where quantum proofs don't appear to help. So for example, the task of approximating the size of a set, right? This is something that is, there's an AM protocol, for it. But if you just sort of have a one-way communication from the prover to the verifier, and all the verifier is allowed to do is just query some membership oracle, a quantum proof cannot help it, approximate whether a set is large or proving that a formula is unsatisfiable, quantum proofs don't seem to help, or certifying that a black box function is 1-to-1 rather than 2-to-1. Again, another example of a problem where quantum proofs don't seem to help. So if QMA is equal to QCMA, then quantum proofs can be efficiently replaced by classical proofs. And there'd be some interesting consequences of this, which I think, a lot of people would find pretty surprising. So, one surprise would be that ground states or minimum energy, minimum eigenvalue eigenvectors of local Hamiltonians, they would actually have efficiently checkable classical descriptions. And, in some sense, this would kind of imply that, like, for physically relevant quantum systems, right, for any local Hamiltonian that a physicist might come up with, the ground states, which are these, minimum energy eigenvectors, they would somehow have limited complexity. Like the types of entanglement structures that you would see in them couldn't be arbitrarily complicated, right? They would, be something that's checkable only using some short classical witness. Or, going back to this circuit equivalence problem, suppose you had two quantum circuits that behave differently, then somehow there'd be a polynomial sized classical witness of this fact. I think, people would find that surprising.
Are these two equivalent? These two bullets? Because like the second one seems less surprising to me, but
Yes, they would be equivalent.
very good.
Yeah, because they're both QMA complete problems. If these two classes are different, then it would really say that quantum proofs allow for verification of more complex statements than classical proofs. I mean, it's not just through packing in an exponential amount of information into a quantum state, because that's not possible. It's something more subtle than that. And I would say that this is kind of the prevailing belief of a lot of folks, is that these two classes are different. Of course, unconditionally separating the two is basically impossible given what we know now. So the next best thing to do is find oracle evidence. And that's what I'll spend the rest of the time talking about. Okay, so let's talk about oracle separations. So what's going on here? We're going to consider oracle models of QMA and QCMA. And this is kind of an analogy to QMA and QCMA that you saw before. But instead of Merlin and Arthur both receiving some instance X, which is some bit string, which is their input to the problem, they're both going to get as input an oracle, some black box that they get to query. Okay. So the way that they find out information about the problem that they're supposed to solve is by making queries to this oracle. So in this setting, there's two complexity parameters that we want to measure. One is the number of queries made by the verifier to the oracle. And number two is the size of the proof received by the verifier, measured in terms of the number of qubits or the number of bits. And in this setting, the verifier's task is to decide whether the oracle that it receives satisfies some property. Think of it as some kind of property testing problem.
And to be entirely clear, in this diagram, the prover also makes queries, but actually, we're only getting the quantum state, right? We don't. we don't care how it's generated.
That's true, yeah. So, yeah, it doesn't really matter that the prover talks to the oracle. It's just some people ask, like, how does the prover know about the oracle? But of course, you're right. We quantify overall a prover.
Are we allowing quantum queries to the oracle in this possible?
Great question. So we're allowing quantum queries. So what is an oracle separation between these two classes? It's a decision problem, but now the yes and no instances are not sets of strings, but they're sets of oracles. And a separation would mean that there is some QMA verifier that decides between yes and no instances of oracles using, let's say, polylog capital N queries and proof size. N here is the size of the oracle. Like think of if you were to write out the truth table of the oracle, or it's basically the number of degrees of freedom used to choose the oracle. So if the verifier makes these many queries to the oracle and receives a proof with these many qubits, then we say has a QMA protocol. And any QCMA verifier, on the other hand, would require at least polynomial in capital N queries and proof size. But actually, I should say or proof size, either or. If you could come up with such a decision language, or sorry, decision problem for oracles, then this would provide a separation, or that illustrates how quantum proofs can be more powerful than classical proofs. Interesting. So what's known? Back in 2007, Aaronson and Kuperberg provided such a separation where they came up with a decision problem about unitary oracles. So here the oracle is some unitary matrix. It's some transformation that a quantum computer can apply. And you're promised that either the unitary is the identity transformation, meaning that it does nothing to its input state, or it's this reflection around some state. So you can think of this as a unitary that it acts as the identity, except on some specific input state, ket psi, it applies a minus sign. Okay, so it's a reflection. And you're promised when one is the case, and you just have to decide. The QMA upper bound should be clear. To prove, in order for to prove that it's the oracle is of the second case, the prover can just send the state ket psi. So it's a collection of little n qubits. And the verifier can use the oracle to check that a minus sign was applied, and it would accept for really in this second case. QCMA lower bound, there is a QCMA lower bound. So think of ket psi as a uniformly random quantum state, right? The verifier has no idea what it is. And this is a random vector in a Hilbert space of dimension 2 to the n, which is extremely large dimensional. And if the verifier is only getting some classical string with only poly little n bits of information, intuitively that shouldn't help the verifier locate where this random state is. So by concentration of measure arguments, a QCMA verifier cannot distinguish between these two cases without making exponentially many queries to the oracle. So that was an example of an oracle separation. And it's a nice separation, but it's not too hard to show. Kind of very, very intuitive. Right? You're kind of exploiting the fact that quantum states live in a very high dimensional space. And if you have a random quantum state that you're looking for, a small amount of classical advice shouldn't be able to help you locate it.
So the way the oracle is queried is that you send some quantum state and the oracle will apply U to that.
So technically speaking, it can apply U or something also called a control version of U. Like you can apply the oracle conditioned on whether a qubit is 0 or 1. That's
and then you cannot measure it. So you would get a different state if you just pick some random state and You will get a state that's not exactly the one you had before, but you cannot measure it, that's the problem.
Yeah, I mean, it won't be exactly the state you started with, but it'll be exponentially close. So yeah, you can't tell them.
I see.
So this is known as a quantum oracle separation, where the oracle here, it's really some inherently quantum operation. It's hiding some, very complicated quantum behavior. And what they followed this up with a question, which is whether there's a classical oracle separation. And here, what they're asking for is an oracle where it actually just computes some function. So some function mappings a domain capital N to a domain capital M. And since the verifier is a quantum computer, it can query this classical oracle in superposition. So suppose that the verifier started with some superposition over inputs, let's say summation over some elements X, where X ranges from the domain. Then after applying the oracle, it gets the corresponding outputs in superposition. So somehow, if you can have a classical oracle separation, that feels like then, it'd be much more interesting because, there's a classical oracle problem. Your yes instances and no instances are just sets of functions, and you're asking for what pairs of sets of functions can a quantum proof help distinguish. And there's been a lot of partial progress over the years. There's some works, in the previous decade, and then in the last couple of years, there's been a bunch of interest. But the problem is still open. Essentially, all of these results assume restrictions on the oracle model on the verifier. This very last result by Mark Zandri from a month ago actually proves a result that's somewhat very similar to ours in that he uses some pseudorandomness conjecture to imply the existence of an oracle separation, but it's a different pseudorandomness conjecture. These first four results are separations based on graph problems. And in particular, this is going to be sort of the foundation for this work, which is, so Ludomirsky proposed something called the components problem, which is to decide whether an exponentially large graph has two disconnected components or a single component. He proposed this as a candidate QMA QCMA oracle separation back in 2011. And then Natarajan and Nurke showed that, they showed that in some variant oracle model, this randomized oracle model, this components problem is actually a separation. And this is the problem that we stick with. Okay? We show that under the pseudorandomness conjecture that I'll get to in just a couple minutes, there really is an oracle separation based on the components problem. So what is the components problem? Let me first define a notion of a graph oracle. So this is some function that takes in two inputs. It takes in what I'll call a color, so some variable r, and a name of a vertex. And it'll map you to another vertex. And it's a graph oracle if for every color, this function defines a matching. So f of r comma x gives you y, if and only if f of r comma y gives you x. So you can just think of, this function really specifies a union of matchings for a graph of size n. The components problem is, given an oracle access to such a function, a yes instance is, the corresponding graph that results from this function. It can be partitioned into two components of size n/2. And in the no instance, it's if the graph is not only a single component, but it's actually some expander graph, okay, some delta spectral expander. And in particular, since an expander, it's a single component that's very, very highly connected. There's no way of dividing the graph into two without cutting many, many edges. We should think of delta here as just some constant, so the number of colors is also a constant, and the number of vertices as being exponentially large in little n. So this components problem is in QMA. There is a way for a quantum prover to prove to a verifier that the graph oracle really is partitioned into two disconnected components. So we know that for a yes instance, there really is some balanced partition. Let's call it S and S bar, and there are no edges that cross the partition. And here's the intended quantum proof. This is what the prover should send to the verifier. It's going to be a uniform superposition over all the vertices, except for all the, there's a minus sign on all the vertices that are in, let's say, the second component. I mean, it doesn't really matter what you call first and second component because it's this state up to a minus sign. So, this is sort of an indication of where quantum power is coming in. It looks like it's the uniform distribution over all vertices, but there's, this minus phase, which is something that doesn't exist in classical probability theory. And this minus phase helps the prover just, tell that there really are these two components. And, this is a quantum state on little n qubits. So how does the verification work? So when the verifier gets some little n qubit quantum state, it's going to perform one of two tests at random. It's going to do a balancedness test. It's basically going to check that it's the state that it receives. I mean, it's hoping that it receives something like this, but it doesn't know. So it's going to check that there really is a minus sign on half of the elements of the superposition. So it's just going to check that this state is orthogonal to the uniform superposition where all the coefficients are positive. Right? This is something that it can do. And then the other test is, and so the balancedness test is to check that, there really is this partition. And then the second test is to check that within these partitions, if you take a random walk within the partition, you sort of keep the partition invariant. So the verifier will pick a random color and then just permute the vertices according to the matching. So the first test checks that you have a balanced partition of vertices, and then the second test essentially checks that there's not many edges that cross between the partition. Of course, there shouldn't be any edges, but.
So what exactly happened in the second one? I'm not sure I understand. So you apply, when you check the size invariant, you just want to apply it and do product with psi.
Right.
Okay, exactly. You want to get one.
You want to get one, yeah.
Well, you can try all colors, I guess, if you think of it as constant.
That's true, yeah. So that's an efficient, verifier. You can check that this QMA verify that I just described only makes one query and it receives a log n capital N qubit witness, which is very efficient. But now we're going to turn to the QCMA lower bound, and assuming this quantum pseudorandomness conjecture, then any QCMA protocol for this components problem must make n to the omega 1 queries to the graph oracle, or receive a classical witness that's essentially exponential in size. Okay, so
How are we counting as I'm not clear about the model. So what you showed us is a quantum state with little n qubits. So that's the log.
Yeah.
What's in the main theorem, what does it mean to make capital N queries? I mean, how many queries are we making here in the
QMA?
Did that?
Just
one, actually.
just one.
One.
Just one.
One.
Just one query, yeah. So
Compute the inner product
full
for me.
Yeah.
That's the query.
that's
Full flanks is the NP.
Okay, thanks.
so there's a huge separate, it's constant query complexity versus essentially exponential. All right, let me get to the pseudorandomness conjectures, because I think to me that's sort of maybe the most interesting part. And now, let's take a quick break from quantum and just think about classical probability distributions. So let's talk about something I'll call a dense distribution. This is a random variable over, let's say, n-bit strings is delta dense. If for all subsets of coordinates, the min entropy of your string restricted to that subset is near maximal. It's 1 minus delta times the size of that subset. So just pictorially, we can pick any subset here. And if you just look at the marginal distribution of bits, you see 1 minus delta fraction of its maximal entropy. And that'll hold for this subset or even just a singleton. Okay. So everywhere you look, this string just looks very dense.
That's called spread in the pseudorandomness. It's just like.
That's usually only when we have like some restricted class of test functions, not testing over all subs. Just that's when
Yeah, but anyway, this.
it's also a lower bound condition, not an upper bound. That's maybe a big difference too.
That's a low bound.
Yeah, that's what I'm saying.
And also in pseudorandomness is low.
No, usually it's upper bound.
That's actually so fun.
So yeah, just a quick example, example of a dense distribution would be, uniform over all even parity strings. This is 1 over n dense. And that's easy to see. Like if you look at the whole string, you're missing 1 bit of entropy. So that's, delta is 1 over n. And then any subset that's smaller than that is actually going to be uniform. So just, the actual pseudo-randomness conjecture I'll use, it's a little more complicated to state, but here's sort of a warm-up to convey to you the spirit of it. So the conjecture is that for all capital T query quantum algorithms, for all delta dense distributions f over n bit strings, the quantum algorithm, if it queries either a string sample from this dense distribution, the probability that it accepts, compared with the probability it accepts when it gets a uniformly random string, is at most polynomial in the number of queries it makes, times polynomial in the denseness parameter. So this gives you a non-trivial bound if delta is smaller than 1 over poly t. Is this so it's basically saying that from the point of view of a quantum query algorithm that doesn't make too many queries to the string, it can make superposition queries to the string. It can't tell whether it's a dense distribution or uniform.
So we're not talking about the runtime of the algorithm. Well, that's the right. Yeah.
Can you show the definition again of delta? Yeah.
So every window, you see 1 minus delta fraction of the maximal entropy.
Why is this not like equivalent to just like a min entropy condition just on X itself? Doesn't that capture?
It's so if you have a string X with some min entropy deficit, some of the bits can be fixed.
Okay, sorry, I realized my mistake. Okay,
but I think what you're suggesting, actually there is a connection. Like every high min entropy distribution can be decomposed into things that look like this. I'll get into that in a second.
Sorry, I thought that you were testing all subsets of 0, 1 to the n, which is not true. That's the right.
Yeah.
Okay.
Yeah. These are subsets of coordinates.
Yeah. Okay.
Yeah, but capital N is to the end. 0, 1 to the end.
So where does this conjecture come from? It's actually motivated by results in classical crypto showing that dense distributions fool classical algorithms that make a small number of queries. And so this is a theorem, not a conjecture. And this was proved back in 2017. Basically, this conjecture is true if you're thinking about classical randomized algorithms. Right? And the advantage that an algorithm has to distinguishing these two types of distributions is delta times t. Which kind of makes sense, right? Like if the min entropy, so any classical algorithm, if it only makes t queries, it just sees that subset, and that subset is going to have 1 minus delta fraction min entropy. So, the statistical distance is at most delta t.
So what the query? What is the answer to the query?
It's just a bit. So
okay, yeah. So this should be a simple thing.
Very simple,
Yeah.
yeah. So it's simple, makes sense, but it's used to, it's useful in crypto to argue that, if you have a random oracle, but some adversary can pre-process large oracle and to give you a short amount of advice, that short amount of advice can't be helpful to help you break some crypto system. Okay, but we're interested in the quantum version of this conjecture, and there things don't seem so simple. So Guo, Li, Liu, and Zhang showed that this warm-up quantum conjecture implies a long-standing conjecture in the late 90s that we still don't know the answer to. This is called I'll just call it the no quantum speedup conjecture. That's just my name, So this says that for all T-query quantum algorithms, there's always some classical algorithm B that makes only a slightly more number of queries that simulates the quantum algorithm on the uniform distribution. Okay, so now this is no longer about dense distributions. It's just saying that if you have a quantum algorithm that queries a uniformly random bit string and has some certain acceptance probability, that same quantum algorithm can be simulated by a classical algorithm with only polynomial overhead. And this kind of roughly captures the intuition that if you wanted an exponential quantum speedup, you have to have it be for a highly structured decision problem. Right, the fact that we're querying a uniformly random string here is kind of modeling this notion of an unstructured problem. So we don't know the answer to this. This could be false, but it turns out that this pseudo-randomness conjecture about dense distributions implies this no quantum speedup conjecture.
And this will be your assumption.
Not this one.
Okay.
Yeah, but. And just because I think this is a really interesting connection, this no quantum speedup conjecture is also implied by the following, which is that this is called the Aaronson-Ambainis conjecture. And this says that all degree T polynomials, bounded polynomials from the hypercube to 0, 1 has some influential coordinate, meaning that the influence of this coordinate J is at least polynomial in the variance of this polynomial divided by the degree. So this looks like it has nothing to do with quantum, but it turns out that if you prove this implies this no quantum speedup conjecture. And this
connection is not so mysterious. I mean, a T-query algorithm can be described by a degree T polynomial.
That's right. Yeah. So yeah, I guess if you know about the polynomial method in quantum computing, then maybe it makes sense. So there's been a lot of partial progress on this question, but we still don't have a resolution. So I've just thrown out a whole bunch of conjectures at you, but let me just sort of draw it out so you can sort of see the mental map.
Can you go back one step? Just a short comment. If you replace polynomials by decision trees, then we do know a theorem saying exactly that. So it's really interesting extension of the decision. Like if you, instead of degree T, you say depth T decision tree, then we know a lot about it.
Right. Also, if we replace T by 2 to the T, then it's using one of Arit's results. Then that is true. There's a whole bunch of conjectures that I just threw, at you. Here's how they're all related. There's this warm-up pseudorandomness conjecture, which is about dense distributions fooling quantum algorithms. There's the Aaronson-Ambainis conjecture, which is just some question about low-degree bounded polynomials. These both imply this no quantum speedup question. And you can wonder, how are these two related? I could have also formulated this pseudorandomness conjecture just to be about polynomials rather than quantum algorithms, right? Saying that dense distributions fool low-degree polynomials. In that case, this would imply both of these, or actually all of these below. All right. So something we do know is, can we get evidence for this warm-up pseudorandomness conjecture? And I can prove a version of it is true. if you assume that the number of queries or the degree of the polynomial is small. So if you have a degree T polynomial P, then for any delta dense distribution F, the expectation of this polynomial on the dense distribution as compared to the uniform distribution is bounded by, some quantity that, here. The important thing to pick out here is that the dependence on T is exponential rather than polynomial. So that's kind of the thing we don't want. If you could get this dependence to be polynomial in T, that would be absolutely great. That's kind of the thing we want. But it does give non-trivial bounds for when, the degree is constant and the min entropy, the denseness is, some inverse polynomial in capital N. So, this Warnock conjecture is not totally outlandish. It is true if you have a small number of, a small degree or a small number of quantum queries. The question is whether you can boost it to be quantitatively better.
Is it important for your conjectures that you can control both sides of the error, or do you only need like an upper or a lower bound for the pseudorandomness conjectures?
You mean instead of absolute value, whether you just have, yeah, but I feel like that shouldn't be, like you can always negate like the output of the polynomial
I see.
algorithm, so it shouldn't make a difference. Okay, so now with that in mind, I'll tell you what the actual pseudorandomness conjecture we use is, and we're just switching models a little bit. We're going to talk about random permutations rather than random bit strings. So we consider algorithms that can query permutations on their inverses. But we can define the same notion of denseness for a random permutation. So if you have a random permutation over capital N, then when you look at any subset S of some coordinates of the permutation, the min entropy of the marginal distribution is 1 minus delta of the maximal amount. And this summation is just the entropy of a uniformly random permutation in that subset. We're just looking at 1 minus delta fraction of that. So the actual pseudorandomness conjecture we use is very much the same thing, except now the algorithms are querying a delta dense permutation. And we're stipulating that an algorithm that queries a dense permutation cannot distinguish it from a uniformly random permutation.
And the permutation will describe the connected component.
Yes. Yeah. So, this conjecture is true again if we restrict to classical algorithms. So it's not, I think, too far-fetched to think that it might be true for quantum algorithms as well. Okay, yeah, and so with all of that build up, I'll just sort of quickly sketch how we use these conjectures to separate QMA from QCMA.
You can run a little over.
A little over time?
Yeah.
Okay, but feel free to, but this will be just a few more slides. So this is the main theorem again, assuming this conjecture about not being able to distinguish dense permutations from random permutations. This components problem is hard for QCMA. And I just want to point out that this is a way that I like to think about our results is that's kind of a win-win situation in that either there is this classical oracle separation between QMA and QCMA, or that the quantum pseudorandomness conjecture doesn't hold. In which case that, there is some quantum advantage in distinguishing dense permutations from uniform permutations, which I think would be interesting. But okay, assuming the conjecture, how do we prove the QCMA lower bound? So let's suppose for contradiction that the verifier V solved the components problem with, let's say, n to the little o of 1 queries and n to the little o of 1 proof length. So now the proof is classical. What we're going to do is we're going to take all the yes oracles. So the yes oracles are just graphs with 2 disconnected components. And each of these supposedly have some classical witness that proves to the verifier that it's disconnected. So for every witness W, we'll just take the collection of oracles, which, for which that's a good witness. And there's going to be some witness that I'll call W star that has the largest number of yes oracles in it. Okay, so I'm just drawing this strange shape because we don't know what shape it's in. But we know that its fraction is at least 2 to the minus q, right? Because q is the size of the witness. And so the first thing we're going to do is we're going to take that, largest witness, W star, and just hard code it into our verifier. So what do we have? We have some algorithm V star. It makes a number of queries, but it no longer receives a proof because I've just hard coded it, the proof. And this V star, this algorithm, is going to say yes on this yellow region of yes instances and reject all no instances. So I've gotten rid of the proof and I've now just reduced this to a query problem. Now I'm going to bring in these permutations. So, and I think as Avi was anticipating, we can view every graph, every yes graph as being built out of a bunch of permutations. So every yes graph, we can think of it as a function of, some permutations I'll call X, Y, and Z. And here's how we think of it. So the first permutation X, which is a permutation on 1 through n, it's going to specify how we partition the vertices. So all of these entries in the first half will tell us which vertices go in the first component. All of the entries in the second half will tell us which entries go in the second component. These remaining permutations are now going to be on 1 through n over 2. It's going to specify a matching within each component. So all the Y permutations will tell us how to match up the vertices within component number 1 for each color R. And all the Z permutations will tell us how to match the vertices in the second component. That's believable. And the point is that if you sample X, Y's, and Z's uniformly at random, that will give you a uniformly random instance of a graph instance of the yes code. Okay, so then what do we have here? We have some V star, which is some algorithm that makes T queries to a graph oracle. We can think of the graph oracle as itself making queries to a bunch of permutations and their inverses. And it'll make, in total, this combined algorithm makes O of T queries, right? So, the number of permutations here is constant. So, there's some constant blow up. And now we're working our way towards invoking the pseudorandomness conjecture. So we have this yellow shaded region, which is all the yes instances that our V star accepts with high probability. And we can sort of look, what are all the permutations that led to it? Right, so these tuples of permutations I'll just draw as this purple region. And the point is that if you think about the uniform distribution over this purple region, this is a high min entropy distribution over tuples of permutations. And the min entropy deficit is going to be log of, so what's the min entropy of the uniform distribution over this purple region? It's, log of the total number of permutations in this this entire area minus Q. Q is the size of the witness, which we're treating as small. Okay, so here's what we can say about that purple region. So since the min entropy deficit is small, we can actually, turns out we can decompose it as a convex combination of random permutations where each of these G sub k's have a small number of fixed coordinates. And then everywhere else outside of these fixed coordinates, you have a dense distribution over permutations. This decomposition lemma is not too hard to prove. You just use some sort of greedy argument. But this is something that's actually showed up a lot in like communication complexity, some crypto, so on. It's a very nice lemma. But the upshot is that we can, this V star, this T query algorithm, we can think of it as querying one of these distributions over permutations where some coordinates are fixed and then the rest are dense. And it will accept with high probability, let's say 9/10. All right, so there's some distribution with fixed coordinates. It's delta dense everywhere, and V star will accept it with probability 9/10 minus epsilon. And now we can throw this at the quantum pseudorandomness conjecture. We can just replace dense with uniform. So this query algorithm V star is just querying some permutation that's uniform everywhere except for some parts of the permutation are fixed. And it still accepts with high probability, let's say 8/10. And we're basically there. So let's sort of think about what's the graph interpretation of this. If you take all these permutations X, Y, Z and you just fix a small number of coordinates, you're essentially just planting some small fixed structures in these two disconnected components. And the rest, everything else outside is just uniformly random. Right, so from the point of view of the quantum algorithm, this is what it sees. And what we're really proving a query lower bound is, can a quantum algorithm tell between whether you have a uniformly random yes instance with some fixed structures, or you have a single connected component with those same fixed structures. And the point is that you can use this algorithm that distinguishes between graphs with these fixed structures and convert it into an algorithm that distinguishes the original components problem without any fixed structures. But there's a known lower bound, which says that you can't do this with a sub-exponential number of queries.
Where are you using the expansion of the non-instances?
That's what we're using both expansion of the yes instances and the no instances. So when you pick a uniformly random graph that's a yes instance, it's an expanded graph in the two disconnected components.
So what is used in the proof?
So it's used to argue that, so it's in this reduction where you have an algorithm that can distinguish between yes instances of the planted structure, and we can turn that into an algorithm that could distinguish one without the planted structure. And essentially we kind of randomly plant that structure in a graph, an arbitrary yes instance.
And what is expansion?
So we have to sample where we want to plant that graph. So we pick a random point and we hope that it's in one of the components. We do a random walk, we plant, and then we pick another random point, do a random walk and plant. So that's basically it. Kind of the main point is we use a pseudorandomness conjecture to kind of reduce to the case where we're just fixing a bunch of vertices and edges in these two components. And actually, even though you fix these small structures, that doesn't really help you distinguish between whether you have two disconnected components or a single connected component. That's the main idea.
Thank you very much. Question.
I guess the only part of the proof where you use the proof is classical is you pick this random or find this W star, right? And I mean, you could do this with the quantum thing, but then you would ignore your entropy exponential size. Like you could hard code a quantum proof, but it would just be much worse.
That's right, yeah.
Okay, thank you very much again.